And gentlemen, we'll continue our showcase lecture with our second speaker for today. I would like to introduce Ben Yang. So Ben Yang is a combinatorist. He finished his Ph.D. at Massachusetts Institute of Technology, so MIT. He has been at the IMO. He has represented China at the IMO back in the day. And he has been with us as an instructor for the third time, actually. He's been with us from the very beginning. So let's welcome Ben.
All right, thanks, Caesar. So we're going to talk about the IMO 2007, problem 6. Well, actually, that's my year. Like I did IMO 2007. So yeah, here's the very simple plan. We're going to talk about the question itself, the statement, some ideas, and then we're going to talk about a research problem that's very similar to the IMO 2007 P6. All right, so here's the statement. So n here is a positive integer, and consider this set. So x, y, z, they are just from 0 to n. X plus y plus z is larger than 0. So that condition actually just removes one point, right? It just removes the 0, 0, 0 point. So actually, it's just a grid. It's like an n plus 1 by n plus 1 by n plus 1 grid with 1 point removed. So that's why there are just n plus 1 to the power of 3 and then minus 1 points. Determine the smallest possible number of planes, the union of which contains S, but does not include the point 0, 0, 0. So without the last condition, the problem becomes trivial, right? If 0, 0, 0 is allowed, then you simply take like n plus 1 planes, like x equals 0, x equals 1, all the way to x equals n, and then that's it. But because of the last condition there, then the question is actually very, very tricky. So it turns out that it's one of the most difficult questions in the history of IMO. Only 7 students got at least 2 points. So yeah, I still remember, like when I took the 2007 IMO, I spent at least 3 hours on this question. Of course, unfortunately, I was not one of the 7 people there. It was very, very frustrating, especially because the first day of IMO, this is like the P6, so day 2. So day 1 also got a very difficult question. It's also one of the most difficult questions in the history of IMO. So yeah, I was not able to solve this, very frustrated. But then, after the test, I talked with my teammates, and I learned that they didn't solve it either. So I felt much better after I learned the news. Right, so here, let's look at the outline of the solution. Assume we can cover everything using, k, which is smaller than 3n planes. So 3n is actually the answer. You just take x equals 1, 2, 3, all the way to n, y equals 1, 2, 3, all the way to n, and z equals 1, 2, 3, all the way to n. So the 0, 0, 0 is avoided, and we're trying to show that that's the best we can do. All right, so here's it's probably the trickiest part of the solution. We need to consider some polynomials. So the first polynomial, axyz, we'll just take the product of this x minus I, y minus I, z minus I. I is from 1 to n. And then another polynomial, b. So remember, we're covering everything using k planes. So each plane, since it's now going through the origin, the 0, 0, 0, so it has the form like ax plus by plus cz minus 1 equals 0. So just take the product of the equations of all those planes. And then we see that now both A and B, they vanish at all of the points in S. right? And then we'll just do one more thing. So we find the number lambda, such that this A minus lambda times B also vanishes at the origin. We're able to do that because the polynomial A is not 0 at the origin, B is not 0 at the origin, so just find the correct ratio, and then this difference, A minus lambda B, becomes 0 at the origin. And also all of the points in our set S. So basically, A minus lambda B vanishes on the whole grid, the n plus 1 by n plus 1 by n plus 1 grid. And that's already a contradiction. Like if you know something called combinatorial non-Snellingsatz, that's exactly what the statement is. Because in this A minus lambda B, we have a term, this x to the power of n, y to the power of n, z to the power of n, and coefficient of that is not 0. And then this contradicts the fact that this A minus lambda B vanishes at the n plus 1 by n plus 1 by n plus 1 grid. So yeah, that's already the proof. It's the proof to one of the most difficult questions in the history of the IMO. So if you think about what's the most important idea in this question, well, you can say it's the combinatorial non-Snellingsatz because the only big theorem that we used here. But rather, I would say the most important idea, or like why this question is difficult, is that diffusion here uses algebraic tools, right? It uses algebraic tools to study this combinatorial structure. So actually, like after the test, our leaders told us about the diffusions, and we all felt like we would have got some chances if someone told us that this question is actually an algebra question instead of a combinatorics question. Because during the test, we tried all of the combinatorics techniques, methods, but unfortunately, none of them worked. Yeah, the summary, algebraic tools can be very, very powerful when studying combinatorial structures, right? So turns out that this is not only the summary of the previous question that we just looked at. It's actually the summary of what has been going on in the combinatorial geometry research world for the past 20 years. Starting from the year 2006, that was when a mathematician published a paper solving a long-standing conjecture using basically the polynomial method. Not just because it's a long-standing question, but also the solution was very short. It was like maybe a 2-page proof. And the conjecture was open for like 15 or 20 years. And starting from then, a lot of breakthroughs were made using algebraic tools. Like when in the combinatorics world, like usually people are trying to prove some bounds, and definitely not easy to get the sharp bounds, right? Usually people improve bounds. Like they get some bound, and then several years, maybe there's another group of researchers, they improve your result, they get another, like a new bound. But then, because of the appearance of some algebraic tools, a lot of breakthroughs were made. A lot of bounds, a lot of sharp bounds were found using the algebraic tools. So for the rest of the lecture, I'd like to show you guys one of such examples. It's a research problem, so it's definitely very difficult, but I think the statement of the question is simple enough for people to look at it, to think about it, or to even appreciate the beauty of the solution. So here's the question. It's called the joints problem. Given n lines in R3, in the space, a joint is a point which lies in 3 non-coplanar lines. What's the maximum number of joints that n lines can form? So this non-coplanar conditions important. So basically, the 3 lines should look like this, like the 3 directions. They should not be contained in the same plane. So I'd like to pause here for a little bit. So I'd like people to think about some examples. Right? Just imagine we have n lines in the space, and think about how we can get a lot of joints from those lines. Any ideas here? Any nice construction? So one way to get a lot of joints is by just looking at a grid. Right? Let's say you have just a set of lines in one direction, a set of lines in another direction, and a set of lines in the third direction, and then form this grid in R3. You can say it's like root n by root n by root n grid, so that you have like n lines in one direction, n lines one direction, n lines in the third direction. So like in total 3n lines. And then we have like n to the power of 3 halves joints from that example. So that's one example. Sorry, if you don't have a lot of joints. So it turns out that it's not the best example, but it's almost the best. There is a way to make it slightly better by considering a set of planes. Let's say we have k planes in general positions. And then those k planes, since they're in general positions, each pair of them will intersect at a line. So that's like k choose 2 planes. And then if we look at a set of 3 planes, they actually give us a joint. Because for the 3 planes, each pair of them give us a line, and those 3 lines will form a joint. So it's like k choose 2 lines, and then k choose 3 joints. So that improves the grid example a little bit by some constant factor. But if you look at if you focus on the exponent of n, then still like n to the power of 3 halves. So with n lines, our best example gives us like n to the power of 3 halves joints with some constant in the front. So yeah, n to the 3 halves. I'd like to know whether it's the best or not. All right, turns out that it's a very, very difficult question. So let's say we have n lines. First of all, we have at most n squared joints. That's a trivial bound because we just have n choose 2 intersections at most. So that's like the trivial bound, n squared. If you only care about the exponent. So it turns out that it's actually already very difficult if you want to improve this n squared to n to the 1.99. it already takes some non-trivial ideas. So already very difficult. Right? And then mathematicians, they were able to improve the bound. So Chazelle et al., actually 7 authors there, they proved, I think it's around 1992, they showed that the number of joints is at most n to the power of 7 over 4. And then progress has been made by Scherrer. He proved that the number of joints smaller than or equal to n to the 1.643. And then later on, also by Scherrer and his co-author, n to the 1.6232. Some weird numbers here, because actually, I think the exponent contains some log numbers. These are just like some estimates. Again, I should mention that the question has a very, very simple statement. But these names here, they're all leading experts in this field, in the combinatorial geometry world. So they're making progress, but you see slowly, and if you look at the numbers we have, there's 1.6232. If you compare it with 1.643, well, it's indeed an improvement, but I think it's also clear that it's almost hopeless to get the sharp bound, right? To go from there to n to the 1.4, n to the 3 halves. And then suddenly, someone, Guth and Katz, I think this is 2008, they proved the sharp bound, this n to the power of 3 halves. Using polynomials, using algebraic methods. So I should mention that before this result, this n to the 7 over 4 or 1.6 something, no one used algebraic tools. So they used, but they did use like very advanced combinatorics, techniques, methods, some combinatorial geometry ideas, and also some extremal graph theory ideas like about forbidden graphs. But then the sharp bound is proved using algebraic methods.
Is this their famous Annals paper?
Yes, it's published in Annals. Yeah. Right, so we're gonna take a look at the outline of the proof. So there's a main lemma. If a set of lines has j joints, then one of the lines contains at most 3 times j to the 1/3 joints. So first of all, I like people to think about a little bit about why this main lemma gives us what we are trying to prove. So why the main lemma implies that if we have n lines, then we have at most n to the 3 halves joints. It's a very simple argument. So the idea is to just remove lines one by one. So if this main lemma is true, then let's say we have n lines, they have j joints, and we know that one of the lines contains at most 3 times j to the 1/3 joints. Right? Let's remove the line. And then we just continue. Now we have n-1 lines. We have less than j joints. So again, one of the lines contains at most 3 times j to the 1/3 joints. All right, let's remove that line. And then we just keep doing that. How many times do we do it? We just do it until there are just no lines. So we just do it at most n times. And then we have removed all of the joints because now there's just no lines. So then we have an inequality. So the inequality is j is smaller than or equal to this number, 3 times j to the 1/3 times L. Because after we remove this 3 times j to the 1/3 joints every time, if you do it like n times, then we have removed all of the joints. So from that inequality, like j smaller than or equal to n times 3 times j to the 1/3, if you rearrange it a little bit, then you'll get j is at most, like n to the power of 3/2. So all we need to prove is this main lemma. All right, and then here's the proof. So assume that each line has more than 3 times j to the 1/3 joints. It's like proof by contradiction. I want to show that it's not possible. This is probably the most important step. Let P be the lowest degree non-zero polynomial that vanishes at every joint. So this is what we're talking about. Like we're using algebraic tools to study combinatorial structures. Right? So we have a set of joints. So how do we study them? We actually find a polynomial whose zero set contains all of the points in that set. All right, and then the degree of P is at most 3 times j to the 1/3. Why is that? So here is like some dimension counting argument. So basically, you can think about the degrees of freedom. So imagine if the degree of P, let's say, is smaller than or equal to a number k, then how many degrees of freedom do you have if you want to write down such a polynomial? Well, basically, we're talking about polynomials in R3, so I have 3 variables, x, y, and z. So each term is x to the power of something, y to the power of something, z to the power of something, and the sum of the exponents should be at most k. So, sorry. Yeah, how many different terms can we have? It's a combination number, right? It's like something like k plus 3, choose something. So we can just count the number of degrees of freedom. And then when k equals this 3 times j to the 1/3, we see that the number of degrees of freedom is actually larger than j, which essentially says we are able to find those coefficients such that our polynomial vanishes at all of the j points. So the 3 times j to the 1/3, that's like the upper bound of the degree of P. So P, the polynomial P, vanishes on each line. Why is that? Because each line has more than 3 times j to the 1/3 joints. Right? So this means our polynomial P vanishes at more than 3 times j to the 1/3 points on each line. But if you restrict P on that line, then it becomes just a single variable polynomial whose degree is smaller than 3 times j to the 1/3. But we know that if a polynomial has degree smaller than 3 times j to the 1/3, but it vanishes at more than that number of points, then it's a zero polynomial. Like when we restrict P to that line. Or in other words, the zero set of P just contains that line. Right, so now we have a polynomial P. It vanishes on each line. So the next part might look, new, maybe to some of you. So the gradient of P vanishes at each point. So this part, you need to know a little bit like college math. So we're taking derivatives of P, and actually some partial derivatives. So why is that? Because P vanishes on basically on 3 lines. If you look at each joint, there are 3 lines going through that point, and the directions of the 3 lines, they're not coplanar. That means those 3 directions actually span the whole space. So if the gradient P vanishes at those like 3 directions, then those 3 directions can actually generate every other single direction. So the gradient of P, which is basically we take derivative of the polynomial P. It vanishes at those joints. And that gives us a contradiction because we assumed that P is the lowest degree polynomial, the lowest degree non-zero polynomial that vanishes at every joint. And now this gradient of P, well, actually it has 3 components, like the partial P, partial X. But they have lower degrees. And those polynomials also vanish at all of the joints. What does that mean? That means the gradient of P, it has to be the zero polynomial, right? P is the lowest degree non-zero polynomial, but now we have a lower degree polynomial. So the gradient of P must be 0, and that means the polynomial P must be a constant. So then we have a contradiction. So that proves the main lemma, and then from the main lemma we have the original result. Right, so again, for this question, like the leading experts in this field, they've been studying it, they've been doing research about it for like 10 or 15 years. They're slowly making progress, but the sharp bound is proven using algebraic tools, algebraic methods, and actually this is the as far as I know, this is the only proof of the joints problem. Like I'm not aware of any proof of the joints problem without using algebraic tools. Well, I guess which is basically the similar situation as the 2007 P6. I don't know whether there is a solution that does not use the algebraic tools there. Cool. So basically that's it. I'm gonna stop here.
All right, let's thank Ben. If you have any questions, please. Raise your hand.
So I have to admit, I Googled a little bit while you were holding your talk, and perhaps you are too humble or something like that, but do you want to say anything about your own results on this problem?
My own results about the problem? Yeah, so yeah, Larry Guth, one of the author of the, who proved the joints theorem. He was actually my PhD advisor. So yeah, I got very interested in this type of question, and yeah, actually like studied some generalization of the joints problem. So there are some natural ways of generalizing the question. You see, for example, you can replace lines with planes. Let's say you have, let's say we're talking about R4, and then maybe we have a set of planes and then a set of lines. We can define joints similarly. So we can, for example, if there's, we can call a point a joint if it's on a plane and also two lines. And we can also, let's say, if the direction of the plane and also the direction of the two lines, if they form the entire R4, then we can call that point a joint. So one question is like, with a set of planes, with a set of lines in R4, then how many joints we have. Yeah, so we got some results similar to the balance for the joint problem. I think the result we got was like almost sharp. So we proved that it's like n to the power of some exponent, but with the epsilon loss. So the epsilon is like, that's mainly from a, like some technical issue of the method. But yeah, it's like almost sharp bound. But yeah, thanks for the question.
Any other questions, please? Somebody here, there in the back? You want to ask a question? I saw your hands. I saw a hand. So. Let's see, any other questions? Please raise your hand so I can see you.
So I didn't get why the degree of P must be less than that number. Where does that come from?
Sorry, the degree of P is
Yes.
less than 3j to the 1/3? Mm-hmm. Yeah, good question. So that's like degree of freedom counting. So so basically, if the degree of a polynomial P is, let's say, smaller than or equal to k, then the number of different terms we have is on the order of, let's say, k to the power of 3. There's some constant in the front. So if the degree of P is like 3 times j to the 1/3, then the number of coefficients that we can play with is roughly this number to the power of 3, which is like 27 times j. We just need that number to be larger than j. So we'll have more coefficients than the number of restraints or constraints. So that means we're able to find a non-zero polynomial, just find those coefficients such that the polynomial vanishes at all of the j points. So basically, vanishing at each point gives us an equation about the coefficients. And there are j equations. And here, the point is that we have more than j variables if the degree is roughly 3 times j to the 1/3.
Okay. Other questions? When I see your hands, If there are no other questions, let's thank Ben again.